Say your typical household current, let's say, runs on 110 volts.
Which is
Okay?
a stupid low voltage.
So if you look at this in terms of a mathematical relationship, and this is, and more you have to focus on what you're holding constant and what you're going to change. So if your voltage drop measured across 2 points, if that stays the same, if you increase the current that goes through it, then what's going to happen to your resistance? It's going to become smaller. Why? You're just dividing by a bigger number, right? So, but here's the downfall to that. That's what I kind of showed you back there. If that's the case, if you're holding, and this is what's going to be important, you focus on what you're holding constant. So, your household typically runs off of the same voltage. But what happens is that, depending upon what the appliance is, like if you're running a toaster versus running a pencil sharpener, a toaster needs a lot more resistance because that's how toasters work, okay? Toasters work just by the same, without the smell, hopefully, of what I just did back there with that pencil, okay? So a toaster works by having a piece of wire just like the electric incandescent or the old style bulbs is. You force so much electricity through it that the wires inside the toaster start emitting heat. That allows you to get toast, okay? So if you want a high resistance, okay, if you want that, and your voltage is going to stay constant, then it's just like, hey, how do you do with that balancing act? Now, but if your voltage can change, then, like for, let's say, for example, if you look at resistance equals V over I, okay? Then if you increase your current and your resistance stays the same, so if you increase your current and your resistance is going to stay the same, then what would have to happen to your voltage? It would also increase as well. So as you go through electricity problems, one of the things that you have to begin to think through is what is staying the same. Is my resistance staying the same? Is my current staying the same? Is my voltage staying the same? Okay, because that plays out completely differently mathematically in terms of what you're holding constant. Now, here's the next equation that involves, I'll just start over. You have R equals rho L over A. So, if you look on page 710 of your book, what it has is a list of what we call resistivities. So, if you go down that list, for example, the resistivity of copper is 1.7 times 10 to the negative 8th, and it has kind of some weird numbers of ohm meters. Okay? Which looks weird, but it makes everything play out. Now, in contrast to that, there's copper. If you go down to the bottom and you have, like, let's say, for example, muscle. Muscle has a resistivity of 13 ohm meters. So what that tells me is that the smaller that number is, the easier it is to get electricity to flow through it. So if you look at a contrast of what we just did, where you had the wires, then that was connected to the pencil, and then wires were coming out the other side. Why didn't the wires heat up?
They have less resistance.
Yeah, they have a very, very low resistance. This is why we use copper in wiring, because it has a low resistance. Someone says, hey, I want you to invest in a graphite wire business. We're going to try and have businesses use graphite in their wiring. Okay? Don't invest in that. Why?
Because graphite has a lot of resistance.
It has a lot of resistance. You are going to have, even if you can get the electricity to flow through it, good luck, it's going to heat up a lot, and you're going to not be very efficient because you have to force that through it. So when you're looking at this, basically the bigger the number is, the harder it is to get this to go through. So, in terms of units, so this is your resistivity, which is in ohm meters. Then you have the length of the wire, which is going to be measured in meters. And then you're going to divide that by your cross-sectional area, which is going to be in meters squared. Everything cancels out. You're left with ohms. Now, this is how this impacts your life. You say, I've never seen this equation before. This doesn't impact me. Sure it does. You're going to charge your phone at night. You have two options. You have one where you have a short cord to charge your phone. You have another one that's 10 feet long. Which one's going to have more resistance?
The 10-foot one.
Yeah, the long one. And think of it this way, is that if you just walk across the hall, oh, I'm just going next door. That has a pretty short path length. You're not going to run into a lot of resistance. Now, if you have to walk from here all the way down to the office, that's a much longer distance. You're going to run into a lot more resistance. So this plays out in terms of even the production of solar energy. So one of the advantages of producing solar just outside of that field is this equation versus producing it at a power plant that's 200 miles away. If you have to ship that electricity 200 miles, you have a tremendous length that you have to ship that electricity. What's going to happen to your resistance? It's going to increase. So you're going to lose a lot of that electricity in that process, just because of the fact that the farther you have to ship, make that thing move, ship it, the more resistance that you're going to have. So we've got a solar plant right out here. It's 100 yards away from the MCA, which is what it feeds. Oh, how much resistance do we have? Not very much, because of the fact that that electricity doesn't have to travel very far. So it's a much more efficient use of that electricity. Now, from an engineering perspective, and this is where the cross-sectional area becomes a part of the story. As the cross-sectional area gets bigger, what's going to happen to your resistance?
Resistance drops.
It's going to go down. But everybody, oh, okay, cool, right, we'll just use big massive wires to ship the electricity. Well, what's the problem with that?
The cost and how are you going to wrap
Alex,
up?
just God, let somebody else answer, please. If you have a big area, just what Alex said, what's going to happen to the cost? It's going to increase. Okay, great. You build transmission lines out of these copper wires that are 1 meter in diameter. Cool. Your resistance is going to be really low. But now you have to bear the weight of 1 meter diameter copper wires stretching 200 miles, and you got to keep those up in the air. Well, that's really not so cool. Get a heavy windstorms, like what happened to Skippy? Well, a wire fell on top. Was he electricity? Was he killed from electricity? No, the wire just fell on top of it.
I
But-
think the wind would, if you could move,
Well, same with the
Like
story. It
wire
knocked over the
wind.
pole. It knocked over the pole. But so that's the balancing act that electrical engineers have to figure out. Okay, at what point does the cost of a bigger wire outweigh the benefits of changing the resistance within the wire? That's the cross-sectional design process that you have to go through. But again, and I look at this because that was one of the decisions that we had to make, was what kind of wire are we going to use to get the electricity from the solar array over to the school? Because it was a relatively short run, we didn't have to buy a whole lot of wire because it wasn't very long. So that was a relatively low cost in terms of the raw cost of the wire. So since that was a short run, and that wasn't going to cost us very much, we were able to buy bigger wire to still stay in the budget. So we had a shorter run, but we bought bigger wire, that reduce the resistance of that electricity coming into the school. Same thing is true on Prey Woodman. Okay, hey, it's right there on the roof of Prey Woodman. That's a really short run to get to where that electricity is used. You don't have very much resistance. Hey, we can put bigger wires on there because of the fact that it's such a short run. Okay, so now we need to talk a little bit about some voodoo. So you've got resistance equals rho L over A. Now, a little bit of voodoo. Speaking of wires, how do you calculate the volume of a cylinder?
Base times height.
Base times height, right?
Pi r squared.
Pi r squared.
Pi h.
So you got pi r squared,
Yes, in this case.
right? Times the length equals your area. True? Okay? So you could also say volume of the cylinder, that's volume, by the way, okay? So if volume equals pi r squared L, and the pi r squared is your area times the length, could I solve this for area and get volume over L? So is volume over length the same thing as area?
Yes.
Yes. So could I come in here and go resistance equals rho L, and then instead of area put volume over length?
Yes.
Can I do that? Is that legal?
Yeah.
So if I did that, I could also rewrite that as what?
Rho L squared over V. Yeah.
Over V. Okay? So if you know what you're, so this might be handy because of the fact that it might say, oh, here's the like for example, this is how this plays out in terms of engineering. You have a certain volume of wire, okay? And you might have like a big thick chunk that's very short, but if you keep the same volume and you draw that out, so you have the exact same volume, but you're just going to change that distribution. So if you're willing to keep the volume the same, then you can look at that in terms of, oh, okay, I'm going to keep the same volume. Then you could solve for this and go, okay, I know how much resistance I could have. I know the value of my resistivity. I can figure out, oh, what length of wire can I get out of that particular volume of wire if I know I want a particular resistance. So literally what you can do is, instead of actually having a certain value of resistors, if you look at these equations, you can change, like the wire, you can change the length and cross-sectional area of the wire to create specific resistance based upon that ratio of length to area. Okay, now, if you look at energy flow, and again, we talked about this yesterday, we're not going to draw this to make sure everybody's cool with how this is going to play out. So if you look at a battery, the top that has a little knob on it, that's always going to be the positive terminal. The easiest way to remember that is that looks like a positive little plus sign. And then it's going to go out and it's going to hit a resistor. So a lot of times with symbols, if you see something like that, that means a resistor. If it's a light bulb, it might be something like that where you would say, oh, there's a light bulb. If it's a capacitor, it would typically be drawn like that where it has a gap to show that, oh, here's the two plates of a capacitor. Now, conventional ideas. And again, don't argue this and go, oh, that's wrong, why do we still do it? It's just how it's always been done and we're not going to change it, just accept it. So the conventional idea of electricity is that it's positive charges moving around. Ben Franklin had a 50-50 shot, okay? He guessed wrong. Didn't know it at the time, but he guessed wrong. And again, we're not gonna change it, it's been around too long. So, conventional ideas is that positive charges come out, they lose the energy going through the resistor or going through the light bulb, and then they end up back at the negative terminal. So the whole purpose of the battery is to recharge the particles, okay, or give energy to the field. So this is why, what happens when you don't charge your phone? What happens to it? What does it do?
Well, you don't get a screen that works.
What happens to your phone in terms of movement of electrons? They don't, okay? Because they're there, it isn't like, my phone's dead, someone stole all my electrons. No, okay? The electrons are there. You go up to a freshman, it's like, hey, what happened to your phone? Oh, it's dead. Oh, man, somebody stole your electrons. Pay me $100 and I'll go find out who did it and get your electrons back. They might buy it. So it isn't that you don't have the electrons, but the electrons just don't have any energy. That would be like you go home and the kitchen is bare and there's no food, and it's just like, oh man, just go to school. No, I just don't have the energy. There's no food in the pantry. That's like having a dead battery. So the sole purpose of the battery is to give energy to the circuit. So in the traditional view of this, the particles come in to the negative terminal. They're hungry. Their lunch pail is empty. They go through the kitchen, they're grabbing Snickers and bags of Doritos and grapes and all this stuff. And so they go through the kitchen and they filled up their lunchbox. Then they go out here and then it's like, man, I gotta fight through the resistor, I gotta fight through the light bulb, through the pencil, whatever that is. It's like, man, I'm wore out, I had to fight through it. So then when you leave, your lunch pail is empty because you've given up, you went through all the food fighting through it, and then you get back here and you recharge your lunch pail. In the modern understanding of it, all you do is just reverse the idea. You say, oh, it's electrons that start at the negative terminal, and it's the same idea. The electrons leave, they come in through the positive terminal. They're, in this view, when they hit the positive terminal, their lunchbox is empty. And then they go through the battery, and then they recharge, and they refill their lunch. It's the same idea, it's just which direction that you're going. So when you're looking at one of these questions, I think it's question number, I don't remember which one it is. Question 9 on today's assignment. So on that one, once you look at this, it's going to say, which direction, clockwise or clockwise, does an electron travel through the wire in 22.9? So on that particular question, when it's talking about the electron, that's kind of the modern understanding of it. Now, if it had said, in which direction does the current flow? So unless you're specifically told, oh, we're going to deal with electrons, if it had said, which direction does the current flow, that would be positive to negative. But since it specifically says, what's the direction of the electron flow, that's going to be from negative around to the positive. Current would be from positive to negative. Okay, I'm done. You're on your own. Oh, Lordy. No, and again, this assignment took me, okay? It's not bad.
Thatcher will be pleased to hear.
Thatcher will not. Right. Too much.
Thatcher will not look at this assignment.
Thatcher
He's
will.
taking GEs.
Yeah, this is
This is just like.
This is beyond.
No, it's not enough way.
Look at the triangle.
What's a triangle?
Tyler, it doesn't really get bad when you do series and parallel. So
Yeah, I know.
and then through analysis. I hated doing
Oh, there we go.
that.
It's over now.
It's not too bad. That's it. I hated doing analysis. That was my least favorite.
He's still looking.
It's still going.
No, I'm just going to give you some hints.
Okay,
No, that's the end of the assignment, right there.
Really, hold on. Converting numbers into binary. I was not sure.
I
Unfortunately.
forgot how to do
It's
that.
the one that you know, you
I know to give it like one,
That's
Yeah,
not.
one,
When you said that
four,
before.
six,
and then
one,
like
two, four,
one,
one, six,
Okay.
64, 128.
one.
This will make sense when you get to question number 29. You have to draw a graph, and you can just draw it on your paper. You don't have to draw it on a separate
But that
graph
was
paper.
today.
But you're gonna draw a graph of ants or current, and you're gonna have voltage on your y-axis.
Draw or sketch?
Well, here, just chill out. You're gonna have two different lines on here, okay? One's gonna be a shorter wire, one's gonna be the longer wire. Make sure you label it so I know which one is which, okay? Just don't draw lines and think, oh, Burkamp will know which one it is. No, Burkamp won't know which one it is, okay? So on 29, when you draw the graph, also pay attention to the units on that graph. Okay, in terms of slope. All right, you're on your own.